Welcome everyone. It's really great to see so many people on here coming to support our young students as they present quantum computing to you. So this is the completion of their 12-week course. They've been working really hard for this young, tender age. It is not a simple subject, I can guarantee that. So thank you for your support for them. It means a great deal to myself and Eamon Darcy. So I'm the founder of the Angel School, which was formed in 2019. The school covers subjects in quantum, metaphysics, and spirituality. The reason we introduced quantum is because we wanted students and young people to understand the links that everything has within quantum. So everything is quantum, including us. And then we also live in a world that is driven with technology. So why not introduce the advanced technology of quantum computing to these young people at such a young age? Quantum computing could actually be very destructive in the hands of some negative person. So our idea of the school is that we get this advanced tech knowledge out to students who could use this technology for the purpose of good, for the benefit of the world and others. And on that note, I would like to hand over to our tutor, Eamon Darcy, the founder of Kwekwa.
Hello, everybody. I hope you can all hear me. Eamon Darcy is my name. As Natalie says, I'm the founder of Kwekwa, which is the Quantum Education Centre in West Australia. And it was about a year ago that I got a call from Natalie. I can't remember where it came through, but she was so enthusiastic and she said to me, "Oh, can you recommend to me the best quantum computer course for like 12 to 15-year-olds?" And I said, "Well, I'll tell you now, there isn't one, but I'm writing one." And then we laughed and joked, and that's how the course came into existence. And it has been absolutely a fantastic journey. And even during the 12 weeks that all the students have been together, so many more things have happened. We've had huge announcements from IBM. Quantum computing is going to change the world. There's no question about that. And not just in the computing area, in all technologies. It really is absolutely amazing. The first thing to remember is that quantum computing is completely different from all computers that have ever been up to now. They're completely different. Quantum means anything smaller than an atom. So we're talking about the incredible small things that we'll never be able to see. Our latest microscopes, although they're electric microscopes, we've just about begun to see an atom. So these are a million times smaller, yet when scientists first found out about quantum particles and then analyzed them, they couldn't believe the powers that they had. And we still don't understand how they work, but we're able to manipulate them to do calculations that are going to change society. But you don't have to take my word for it. Natalie, can we have the next slide, please? Okay, let's see what Jeff Bezos is saying. And of course, he's the founder of Amazon. He's doing his space stuff. You know, he's obviously one of the top commercial people in the world. He says, quantum computing is the future. I am not exaggerating when I say it will change everything. Now, that's a very insightful statement from a very insightful man, because it will change everything. And the students today will give you an indication of why and how that will happen. But I've been in this industry a long time, and only 10 years ago, I had people saying that we would never, ever have a quantum computer because it's too hard to control. And here we are, just a decade later, and quantum computers have already outperformed the fastest classical computers we have. But you're going to hear more about that later from the students. Natalie, can I have the next slide, please? Okay. Natalie, when she approached me, she said what she wanted to do was encourage the morals and ethical values of the students and teach them in a way that they, as Natalie alluded to, quantum computing is going to change everything. And like any technology, it can be used for bad as well as good. So we need more people who are moralistic and full of ethics to be in control of this technology. When I put together the 12-week course, these are the 5 rough areas that I got involved with. First of all, the first few weeks was about the mysteries of quantum physics. And a couple of the students will, I think 3 or 4 of them, will be taking you through this. And if you don't know anything about quantum or subatomic particles, you are going to be amazed. And you're going to be even more amazed that you are made out of quantum particles, as is the desk, as is your house, as is everything. In order to talk about quantum computing, we have to talk about the very mysteries of quantum physics and the fact that nature is quantum. Nature is a billion transformations every millisecond. And believe it or not, the quantum computers can handle this exponentially. And one of the students will be talking about that later. So there's all these mysteries, basically superposition, quantum entanglement, and quantum tunneling. And the students will tell you about them very shortly. Quantum computing, okay, so these mysteries are unbelievable, but how do they do computations? And that is unbelievable that we've been able, mankind has been able to master this technology that we don't fully understand. It's mysterious, it's weird, yet we can use it to do what we call intractable calculations and computations. Computations that we never ever thought would ever be able to be performed. Then we'll talk, then there's a couple of classes on linear algebra. Now, if there's any engineers in the audience, and I know there's a couple, let me apologize by saying linear algebra was the domain of engineers. They're the only people, who cared about it. But unbelievably, these strange forces and the strange computations we could mathematically represent through linear algebra, through complex and imaginary numbers, and the guys will tell you about that soon. Fantastic. Then we talked about comparing classical and quantum, and we want questions at the end, but this is a great way for you to compare the two and the world, the futuristic world we're going into. As I say, IBM just 10 days ago made an announcement that's changing the world. We now have a computer that the fastest digital computer on Earth cannot simulate anymore. We're already going into a different level of existence. That might sound over the top, but like Jeff Bezos says, it's going to change everything. So let's compare classical and quantum, and the guys will do that. But it's not all plain sailing. Why don't we have a quantum computer now? By the way, there are many of them in the world. Let's get that straight. In fact, there's one here in WA. So quantum computers are real, they exist, but they aren't doing anything particularly functional at the moment. But there are obstacles, and the students will tell us what they are and what they've achieved. So Natalie, if I can pass over to you now, and we'll start the presentation.
Hi there. I'll be introducing to you light rays and what they have to do with quantum computing. Please move on to the next slide, Natalie. In 1801, there was an experiment called the double slit experiment, where a scientist put many light rays through a double slit and put a board behind it, which showed the results of what would happen. Now, as of course you'd expect the rays to pass through a double slit, and on the board, which shows the results, you'd expect two little light rays in the shape of double slit. But a wave pattern was formed, also known as an interference pattern. So for about 100 years, people believed that light was a wave and not a particle, until Einstein did his own experiment to do with light rays. Please move on to the next slide. And in 1912, Einstein shot light rays onto a sheet of metal and off reflected electrons. Now, that doesn't make any sense. Why does light in one experiment show an interference pattern, but in another, it shows that light is a particle? This doesn't make any sense. People were confused, people were baffled for about 20 years until they thought about it properly, and they realized that it's not one, it's not only one, it's both of them at the same time. So they dubbed that wave-particle duality, until they simplified it down to what we call superposition. Now, superposition basically means the particle is everywhere. But that doesn't mean it's physically everywhere, but it means that it has the potential to be everywhere. Thank you very much. And now I'm going to pass it on to Aidan.
Now I'll be talking about what a subatomic particle is. A quantum particle is classed as a subatomic particle, which means it's a particle smaller than an atom. Did you know we are made up of trillions of subatomic particles? Quantum particles display a non-local quality, which is like having your body in different parts, like having different parts of your body in different places, in different worlds as well, which is still able, controlled and coordinated from anywhere in the universe. If we are entangled two particles and sent to one particle and sent one to the planet Mars, the two particles will mimic each other perfectly. Albert Einstein referred to this to a spooky action at the distance. Next slide, please. So the big question is, will we be able to teleport instantly? Large objects, or even humans, to a location or another universe, just like the one on the science fiction movies. Distance and time doesn't exist in the quantum world. If we can teleport physical matter, will our memories and consciousness follow? These are the right questions that quantum science are trying to answer. I'll be now passing it to Matthias.
Next slide, please. So what is a qubit? A qubit is a quantum particle in superposition. Whilst a regular bit can only be 1 or 0, on or off, a qubit can be 1 and 0 at the same time and represent complex and imaginary numbers, which helps it perform complex computations that a normal computer may not do. Next slide, please. This is a slide from the IBM Q experience, which is the main program we've been using in our lessons. And at the top, there's there's gates which you drag and drop onto these lines, and each horizontal line represents a qubit. These qubits will calculate the probability of something happening to the qubit. Chris will be expanding on this.
Next slide, please. So a qubit gate performs state transformations on qubits. So, like Matthias mentioned before, this program is called the IBM Q experience, and using this program is just a simple case of dragging and dropping. There are many state transformations you can play with on this website, but the main ones are the Hadamard gate, which is the H, which puts the qubit into superposition, and then when you want to entangle two qubits, you would put a Hadamard gate followed by a CNOT gate, which is that plus right there. Entangled qubits can perform multiple operations at the same time, and this is called multiprocessing. And when we have 300 qubits, a quantum computer will be able to reference the equivalent of every atom in the observable universe. Next slide, please. So this right here is a quantum algorithm, which is a collection of quantum gates. Superposition and quantum entanglement are the secrets in the amazing computational power of quantum computers. The quantum algorithms are read from left to right like a musical score. Now I will pass it over to Justin, who will talk about linear algebra.
Next slide, please. Just as Krish has said, I will be talking about linear algebra. Linear algebra is when quantum gates are using matrices to multiply, which will cause the qubit to change its quantum state. Most qubits are initialized to 0 at the start, and matrices can get very complicated at points. On the right-hand side of this slide, there are some examples of matrices and what they'll look like. Next slide, please. As shown on this slide, to multiply matrices, you must multiply the rows of the first matrix by the columns of the second. The number of columns of the first matrix has to be equal to the number of rows of the second. I will now be passing over to Ty.
Hi there, I'm presenting to you yet again quantum Earths and what they have to do with quantum computing. Next slide, please. Now, there's many interpretations of how you can represent superposition, the complexity of quantum computing. It's very complex, so people will come up with ways to simplify it down for everyone else. One of these ways is the classical Earth and the quantum Earth. Now, the classical Earth can only be on or off, 1 or 0. You find this as a bit can only be 1 or 0. And what it's basically trying to say is that a circuit can only be on or off. There's not really much it can be apart from on and off. So there's a limited amount of things we can do with this sort of on and off system. But in comes the quantum Earth, which changes everything completely. Next slide, please. Now, it's very confusing, I know, but the quantum Earth can be anything. It doesn't have to be on or off. It can be on and off at the same time, as Matthias mentioned earlier. It can also be complex numbers, imaginary numbers. It can be linear algebra. And linear algebra is actually used to handle these complex and imaginary numbers. Now I'll pass it back on to Matthias. Thank you very much.
So on the screen is an analogy of the classical Earth as a bit. The classical Earth is a binary, so it can only be 1 or 0, on or off. Each Earth doesn't have a real connection between each other and can only perform one operation at a time. Whereas for quantum Earth, next slide, please. Through quantum entanglement, there's a real link between each Earth and can perform multiple operations at the same time. I'll be passing on to Justin for slightly more explanation.
If a 6-digit number had to be guessed, a quantum and classical computer will do this in different and separate ways. Just to explain this, I will be using the quantum and classical Earth analogy. Next slide, please. If the classical Earth had to guess a 6-digit number, it would evaluate one digit at a time and would also need one operation per digit. However, if the quantum Earth had to guess a 6-digit number, it would evaluate the whole 6-digit number at once and only needed one operation for the whole number. I will now be passing over to Aidan.
Next slide, please.
Now,
Why don't we have pure quantum computers today? Subatomic particles are very fragile and it keeps collapsing. It interacts with the environment. Noise or decoherence affects the behavior of the quantum particle. We only want interaction with another qubit. We need a new approach when it comes to the understanding of quantum science. Maybe science from the angles.
Or maybe someone from the angel school.
Maybe someone from the angel school could be the next generation to help pioneer new understandings. Next slide, please.
Quantum supremacy is in a way just as the name expects. It's when a quantum computer can outperform classical computer. This has been achieved on several occasions, starting with Google in 2019, where Google used a 53 qubit chip. But due to noise, all but one of these qubits were used. Next slide, please. So you might not know this, but the processing power of qubits is unbelievable. For example, when you were next using an ATM, you were safe. The fastest classical computer would take over 500 million years to get your PIN. But a quantum computer using Shor's could get your PIN in 6 seconds. So basically, Shor's algorithm gives you the factors of a large prime number, like a very big prime number, like a 1,000-digit number, and then evaluates it. So now I'll pass it back to Eamon and Natalie.
Wow. Look, absolutely fantastic. Thank you, all of the students. These are the future of where we're going at. And so I know Natalie and I are so pleased for what you've done. And we've just got Vigneshwaran, an Indian quantum computer scientist, saying, well done, guys. And I think everybody will be very impressed with that. Now, the audience, do you have any questions? I know, George, you're with us from the US. It's so good to see you taking the time. I think if you can unmute yourself and ask a question, and one of the students will answer for you.
Oh, hello, Eamon. Thank you for inviting me. I'm having a problem with the video. Oh, actually, can you hear me?
Yes, I can hear you, George. Natalie, George is saying he can't actually see the screen. I don't know. We may just have to carry on at the moment, George, which is a great shame.
Since it's being recorded, I look forward to seeing all of your slides later.
Yes, indeed. Do you have a question, George, for one of the students?
Not really. I'm impressed with their presentations, even in audio.
Oh, that's wonderful. Thanks, George. What time is it there, George?
It's 8:30 in the morning.
8:30 in the morning. That's wonderful. Nice. Thank you very much, George. Great to hear from you. Does anybody else have a question?
Hi, hello. I'm Jersey. How are you?
Oh, hello, Dr. Gautam from India. How are you?
Yeah, I'm good. Hi, Natalia, and hi, hello, everyone. Good evening.
Yes, Dr. Gautam, can you tell us quickly what you're doing in the quantum world and ask a question?
Yeah, definitely. Yeah, I'm a founder of Curious, and definitely I had a PhD in quantum computing, and my entire journey is almost. I have written so many research papers on quantum, and some project is also. But I have some little bit question regarding quantum gates for Chris. Hi, Chris. How are you? Chris, this is simple questions. You are talking about the Hadamard gate. So, what exactly the problem of the Hadamard gate if the two interaction picture is coming? If the two states are interact with each other, is that Hadamard gate is a unitarity or not?
Can I pass this question on to Eamon, please.
Yes, I'm not sure, Dr. Gatt, that he can answer that question.
I'm so sorry.
Yeah, that's a
Yeah,
little bit advanced. I
yeah,
thought
I'm
it was.
sorry.
No, I totally understand. Krish, I was really pleased when he mentioned that the Hadamard gate puts the qubit into superposition. And as you know, Dr. Gazan, that's exactly what the Hadamard gate does. And in fact, Justin showed us the formula for the Hadamard gate, 1 over square root 2, 1, 1, 1 minus 1. So yes, it was really lovely. Ty, did you want to say something, Ty?
I can answer
Thank you so much.
the that was asked about what challenges we faced when we first started. At least myself personally, near the beginning of it, since I deal with some code and stuff already, there are parts of it which I kind of understood, like the idea of the on and off, because I was like, oh, that's just a bit, I know this stuff. But definitely at the beginning, something I really faced was just like, it's a lot of it was a lot of information and a lot of things that you would never really hear normally. For example, superposition. It's doing two things which shouldn't be doing at the same time. It's being true and false at the same time. What does that mean? And also, it's just a lot of fancy words that be introduced to you, such as superposition, entanglement. If you don't hear one of these words, they get used quite a lot. So if you don't hear the word / understand the word, it's really hard to keep up. There have been many sessions we've done where we've kind of spoken about all these other things, like I finally understood what a subatomic particle was, but for ages I just hear it and it would just pass through me because I never understood what it meant, and it was hard to understand a lot more. At least that's my own personal challenges I faced, but it could be different for everyone else. Thank you.
Is there anyone else who'd like to answer that question? So the question was, hi boys, do share what challenges you faced when you started your journey in learning quantum technology, and how did you get over it?
Well, I can answer for me. So basically, I first attended the live session, I think at the end of August, and I was completely confused with all the words. But then when I started the course, Eamon and Natalie, they both broke it down really well, and they explained it very well, and then I started to understand it more. And like all the words seemed like so complicated at first, but when they were broken down and explained, I finally understood more about quantum. So I want to thank Natalie and Eamon, who have been great teachers.
Thank you, Krish. And then there's another question. Anyone want to answer this one? I am 10 years old and I want to know, please, what must I learn to help me prepare my mind to help with the huge learning curve that is expected when it comes to understanding quantum computing? One can get lost in trying to grasp that physics. It's super important. Anyone, any student want to answer that one, Ty?
Yeah, when you want to understand quantum computing, I think my own personal advice is not to rush into it and try and learn just quantum computing. Imagine quantum computing being a massive line, right? And this line has many branches which come together to create this line. Quantum computing is made up of math and all these other scientific elements. For example, learning what a bit is. If you know what a bit is, it'll be easier to understand what we mean when we talk about on and off and things like that. It's just break it down for yourself. Don't focus on learning these big words, but learning what is around the word as a whole. For example, superposition, it might be easier for you to understand it if you knew the fact that it was originally called a wave particle duality, meaning a wave and a particle being the same thing. But if you just try and learn superposition, it might be hard to understand it. Break it down, take it slow. Don't just focus on putting your attention to just the line of quantum computing, but focus on the things that are around it. It makes it so much easier, honestly. I hope that helps.
Anyone else want to add to that? How you found it, how it helped to learn, what you did to help you to learn all the technical terms at your young ages. Or we can say, Eamon, what we do to help the students to understand all these big words.
Yes, would you like me to say a few words, Natalie?
Yeah, sure.
I really don't need to, because Ty summed it up beautifully. Take it easy and learn it slowly. The sort of problem we have, what's the problem? The challenge we have teaching quantum computing is that very often, like Ty alluded to, we have to talk about something that doesn't happen in our normal world. So let me explain. If I was talking to you about gravity, which is classical physics or Newtonian physics, I could easily demonstrate it to you. I could throw a ball up in the air and it would come down. But when we talk about superposition, when we talk about a subatomic particle has a probability of being here, there, and everywhere, and it's a wave and a particle at the same time, you've got nothing to hold on to. So that 10-year-old who asked that question, oh my Lord, well done, asking people what's the best way to learn it, because you are at a great age to learn. And it really is a challenge, but honestly, it's not so bad. The other thing is we use an analogy, which is just like a story. So when you've got something that's very complex, if you can make up a story about it, it makes it easier. So when Ty was talking about the classic Earth and the quantum Earth, and it was visually, you could see the differences. So we use analogies as well, stories. Anything you'd like to add to that, Natalie?
Yes, I want to say that we extend our courses, so we add extra weeks than the average 17 or 18-year-old student might receive. So we add extra weeks to the course so that we can spend time ensuring that the students are understanding all the different concepts, so we don't rush them through the course. And we also make it possible for them to reach out to us anytime. They can contact Eamon directly if they have any questions. We also provide them with another platform where they can go in and just revise the work that's been covered and do some more research, all to help them, the younger ones especially, to be kept in touch with what's happening and to stay on the same line as the older students. And this 10-year-old also has another question. He says, where can quantum computing be applied now? Is it only calculations or is it development of end of product? So basically, what can it be used for now? Is it only still in development? Anyone, Krish?
Well, as you may well know, that all these big companies like Google, IBM, and places like China, they're all investing in it. And even though it might not be widely known right now, very soon, quantum will really change the world, just like Eamon said at the beginning. So you should learn it now, because soon it will be a big thing. And if you know quantum computing, then you'll have a lot of job offers, and it can help you get a really good job. And you could become like one of the quantum leading computers in the world.
Anyone else like to add anything to that? Okay, next question. Someone says, well done to all the presenters today. Do the presenters have any particular wish for any practical invention that could make a significant change in our society in the next few years? So anyone have a particular wish for this technology? that you have in mind that we could do for the Earth or for others right now? Yep, Justin?
I'm hoping that like quantum computers could help us do things that right now we could see as impossible. So maybe it could help us with like advancing technology and advancing like healthcare or anything. It would almost be like a massive leap forward for humanity almost.
Good. Anyone else like to add? Thank you, Justin.
I actually struggle with that question. It's a very hard question to answer because there's a lot of things which could potentially improve the world, and it's also just it comes at the price of also being something that it needs to be controlled. For example, quantum computing, as amazing as it is, it needs to stay in the right hands. The moment it's gone into bad hands, it could be the end of the world as we know. So it's just, there needs to be a very strong control on these things. I was going to answer something that Nate also said earlier on. I just need to remind myself. Oh no, I believe that you said, oh yeah, is it only calculations or is it development of an end product? I don't know if it was already said, but it's the development of an end product. I think that's what Chris said earlier.
Natalie, could I say a few things?
Sure.
Yes, what quantum computing is exceptionally good at are two things particularly. One is simulation and two is optimization. Now, when it comes to simulation, because quantum computing is exponential, it can simulate things that we've never done before. Let's talk about obviously the COVID-19 virus we have at the moment. Now, the vaccines, people say, oh, sometimes they're not very good. And the reason is because classical computers today cannot simulate the changing evolution of an atom or the exchange of electrons. They can't simulate them because simulating an exponential is very, very difficult. I always use the example, if you've got a table with 10 people sitting around the table, the amount of different ways you can place those 10 people is 3.6 million. Now that's just 10 people at a table. It's a good question if you're organizing a quiz night, but that's the truth. There are 3.6 million ways. So when you get two atoms or two molecules, there's a thing called protein folding, which is how molecules evolve. We've never been able to simulate this stuff before, but now we can. Now, when it comes to optimization, there's a thing called the knapsack problem and the traveling salesman problem. And these are things that when you want to optimize a certain number of resources, it's surprisingly difficult to do. Same thing as the 10 people sitting at a table. If you are visiting 10 cities to do a sales conference, to know the best optimum route is very, very difficult. Optimization, I happen to be dealing with a company that can optimize your freight for these large companies, like British Airways and Qantas. They have to optimize the freight for the dimensions, for the stability of the aircraft, for the amount paid, the length, the depth, the breadth, the height, the heat, all of these things to optimize, current computers can't do, but quantum computers do it instantly because nature is quantum. So that's that, Natalie.
Thank you, Eamon. Okay, we have one more question. What is the most interesting thing about what you have learned?
Great question.
We should all be able to answer something.
Yes.
I really wanted to speak about definitely quantum teleportation, because there's a lot of things that are interesting to do with quantum computing, but a vast majority of them are hypothetical. It's like, you know, it could be this, eventually one day it'll be able to crack a security pin in 6 seconds. But the thing is, all of that is will, but nothing that has been done yet. Now, by far the most interesting thing I think about, yeah, I'm sure a lot of us want to teleport to the beach, especially in England. It's a long drive, but definitely it had to be the fact that quantum teleportation exists and has been done. Back in 2016, there was the experiment or something to do with sending a particle from a base in America or somewhere on Earth into a space station. And if you ask anyone, when do you think we'll be able to teleport? 100 years, 1,000 years. It's already been done. They sent the particle from that station on Earth, and they sent it all the way up to that space station, which means that teleportation has been done. But yeah, of course, I believe you mentioned this, that there are many potential challenges that may occur. For example, if we teleport a human, will we keep our memories? Will we get there intact? And a lot of other things. But I just think that's super interesting because it's already been done 6 years ago at that. Isn't that crazy? It may be a particle, but it's still a step in the right direction. That by far, I'm sure a lot of us will also have different answers, but I think that might have been a lot of our favorite things. Thank you.
And Aidan, did you have something you wanted to add about what's the most interesting thing that you have learned so far?
Probably the most cool thing that I've learned so far is about what Ty just said about the teleportation with the particle. Photonic light particle.
Thank you. Anything else you want to add to that, Aidan, or is that enough?
That's enough.
All right then. And Chris, your hand is up.
I think for me, the most interesting thing is that when you try to observe, it collapses in quantum. And that's very interesting for me. Like, if you try to observe it, it collapses.
Yeah, that is very cool. That it just collapses. It takes on like different function just from being observed. So what does that say about quantum particles then being observed? Like they change their behavior when they're observed. And we're made up of quantum particles. What does that mean for us? Very interesting stuff. The collapse of the wave function, that's what it's called. Okay, anyone else got any questions?
Natalie, you may just say that we are doing a course on quantum consciousness because it's something we always get asked. The first thing to realize is that we don't understand scientifically how these forces, these quantum forces work. We don't know why when we observe them, and observes the wrong word, when we measure them and measures the wrong word, we don't know what we do to them. And but somehow, let's just say when we observe them, they collapse. It's as if nature is deliberately not telling us what is causing this collapse, and because we try to examine superposition more so that we can understand it. But as soon as we do, it collapses and prevents us. Now, soon our world will be controlled by these forces and we don't understand them. We're desperately trying to. And the crazy thing is that, as Natalie has said, and the students have said, we are made up of quantum particles. If I could somehow put my fist inside you, take out 2 particles, entangle them, put one on Mars, like Aidan said, and one here, and I change the spin of one here, the one on Mars will change instantly, immediately. Something's happening faster than the speed of light, which is why Einstein didn't like it. And he called it spooky action at a distance, like someone said. So look, we don't understand, but we're trying to. Quantum field theory is the best explanation we have of the universe?
Some very high level questions in the chat, Eamon.
Okay, Natalie, you'll have to read out the questions from the chat because I'm a bit behind.
Okay. But it's more of a discussion.
Yeah,
So some are talking about consciousness and how
yeah,
we are the observers, we are the creators.
yeah.
Somebody else also asking about our next courses. So in January, we will be starting a beginner's course all over again. However, this will be during the daytime because we have a lot of people interested in a home education class. So this will be during the daytime. And then we have our intermediate course, which all of our current students would be applicable for. That will run on Sunday morning, starting in January. And then obviously we will introduce another weekend beginners class at some point next year. Okay. Anything else you want to add, Damon?
Oh no, I do want to add how fantastic the students spoke today. They showed their knowledge, they showed their enthusiasm, they showed that they have, you know, to think that 12 weeks ago they knew absolutely nothing. I cannot believe how fantastic their answers have been, how insightful. You know, when someone said, what was the one thing that, you know, surprised you on the course, and someone immediately said quantum teleportation. I thought that was fantastic because it is. I can only stress again that we don't, these forces are real, scientifically proven, they happen, yet we still can't understand how they happen. It's been fantastic. It's been a wonderful journey. And Natalie, you've been fantastic to work with. And I'm looking forward to next year already. But what I'm looking forward to is keeping this group focused on the next step. We always have, what can you do next? Because there's so much more that one can learn about this stuff. You never stop learning. I'm sure the physicists in the audience will agree that you never stop learning this stuff. I'm reading papers and watching university YouTube posts every day. It is fantastic. And we've only touched on these subjects, and to see these very bright, very gifted students pick it up like they have, it's just, I know I speak for Natalie when I say both of us are just, we're very thankful that we've met such a team of bright individuals.
Definitely. And I'm really happy that we're just managing to spark a little bit of critical thought and awareness and deeper thinking in these young individuals who, instead of just looking at their sofa, like most children their age, will look at their sofa and see quantum particles. You know, that is not average. And that is our way of encouraging deep thought and being more conscious of who you are, what you're doing and what you're saying and what's possible for you, since you are made up of a quantum particle that lives in a state of possibility. What does that mean for you? So thank you very much. I don't think we have any more questions. Yeah, that's it. Eamon?
Yeah. Okay, well, again, thank you, Natalie. And let's look forward to next year. And, you know, this is, I believe this is the only school for 12 to 15-year-olds. And we just want to continue, you know, the development of these wonderful, wonderful young people. Thank you all.
Thank you. Goodbye. Thank you for coming. Well done, boys.